PhyAug, physics-directed data augmentation for deep sensing model transfer in cyber-physical systems. This work is collaborated with Yan Zhenyu, Song Qun, and Professor Tan Rui at Nanyang Technological University of Singapore. We are in the age of artificial intelligence of things. Artificial intelligence of things integrates AI capabilities into IoT devices to form an intelligent and connected system. IoT connect billions of edge devices and generate tons of data every day. AI transform the data into smart decisions and empower the IoT with smart sensing capability. However, two main challenges arises amid developing AI solutions for IoT sensing application. First, IoT sensing applications are lack of massive labeled training dataset. The great success of deep neural network rely on massive labeled training dataset. However, IoT sensing applications are lack of such dataset due to inseparable data collection and labeling phase. In computer vision and voice sensing application, data samples are easily interpreted by human. Human assistants are often involved for labeling after raw data collection is completed. Multiple crowdsourcing platforms are already well established to involve human effort for data collecting and labeling, such as Amazon Mechanical Turk. Nevertheless, IoT sensing data can be hardly interpreted by human if merely looking at the raw data. In practice, the labeling process is performed in tandem with data collection phase. Therefore, collecting labeled training data for IoT sensing applications is either laborious or unpractical. The diversity of IoT sensing system introduced a second challenge, data heterogeneity. It's always challenging to find a common feature representation for heterogeneous dataset. For example, in human activity recognition task, the sensor data collected for same activity, like running, can be affected by various factors, including genders, age, sensor qualities, and so on. So far, we have introduced general challenges in applying artificial intelligence in IoT sensing applications. Next, I will present a specific problem we aim to address in our paper and propose our approach. Runtime domain shift problem is very common in IoT sensing applications. This phenomenon results in the scarcity of labeled training datasets for IoT sensing. Because training data collection in target domain is either costly or infeasible. Domain shift can be caused by either sensor characteristic variations. For example, IoT microphones respond to the same excitation differently, or the discrepancies between the design phase physical model and the test phase physical model, like Wi-Fi signal heat map variations. The concept of transfer learning is desired to address a domain shift problem. However, prevalent transfer learning approach relies on machine learning techniques. They are physics regardless. This approach can reduce the demands on the target domain training data in comparison with learning from scratch in the target domain. However, this approach still demands substantial training data from target domain. A key observation in cyber-physical systems is that the monitored processes are often governed by certain first principles. Exploiting the first principles as a form of prior knowledge could potentially reduce the demands on target domain for model transfer. The key question is how to explore the first principle as a form of prior knowledge. In machine learning, physics-constrained learning is a cluster of techniques that attempt to incorporate a prior knowledge to increase the learning efficiency. For example, prior research incorporates the free-fall law and fluid dynamics equations into the loss function of deep neural network. However, this approach requires new network architecture or training algorithm design. Such physics-constrained approach are lack of generality. Current deep neural networks have found many successful applications. We do not want to discard the legacy deep neural network. Therefore, we would like to seek an approach which explores the first principle as a form of prior knowledge to reduce the demand on target domain data for transferring the legacy deep neural network. I will introduce our approach, physics-directed data augmentation for deep sensing model transfer. I will use a simple example to illustrate approach workflow. At design phase, a classifier is used to perform a two-class classification task. During the test phase, first principle governed domain shift. A linear polynomial transform is applied on the source domain data, produce a new target domain. If we apply the pre-trained model on target domain data, we will see the erroneous result. The general transfer linear approach discards the first principle and draws data samples from both the source and the target domains. In general, this approach requires excessive data collection in the target domain, incurs undesirable overhead. Differently, we apply PhyAug in following 4 steps to avoid extensive data collection in target domain. First, the system designer identified the parametric first principle that governs the domain shift. In this example, the parametric first principle is second-order polynomial transform. Second, a small amount of unlabeled data pairs are drawn from the source and target domains to estimate the parameters of first principle. In this example, the minimum number of data pairs needed is the number of unknown parameters of the polynomial transform. Thirdly, all the existing source domain training data samples are transformed to the target domain using the fitted first principle, forming the augmented training dataset. With the augmented training dataset, machine learning techniques can be employed to transfer the existing deep neural network built in the source domain to the target domain. A straightforward way is to retrain the deep neural network with the augmented training dataset. We evaluate our approach on 3 case studies, including 2 voice sensing applications, keyword spotting, and speech recognition. The third case study is seismic source localization. Due to the time constraint, this case study is not covered here. Convolutional neural network can be used to classify speech commands. In this case study, the raw audio data are first converted to male frequency substrate coefficients, then used to train a neural network. We achieve a 90% of accuracy on standard dataset. Subsequently, we use a speaker to play back the speech dataset in a quiet room. 5 microphones labeled from M1 to M5 are placed at an equal distance to collect the data. Then, we evaluate the microphone data on pre-trained model. We observe a 14 to 19% absolute accuracy drops. In this case study, the problem statement is how to explore the first principle to recover the keyword spotting's accuracy. PhyAug explores the first principle to recover the model accuracy loss. It consists of 4 steps. First, we identify that the main contributor to domain shift is microphone heterogeneity. A microphone is often characterized by its frequency response curve. We let X and Y denote the microphone's input and output in frequency domain. The frequency response curve to characterize a microphone is expressed by Y over X. We propose a fast microphone profiling approach to estimate the frequency response curve in a short time. A loudspeaker is placed to the target microphone and emits a band-limited white noise. The signal is recorded by the target microphone. The white noise has a nearly constant power spectral density. This approach can profile the microphone's response at all frequencies in a given band. At step 3, we use the derived frequency response curve to augment the training data samples for target microphone domain. Precisely, we apply the short-time Fourier transform on raw audios to produce 101 Fourier frames. Then, we multiply the magnitude of each frame with the frequency response curve to produce a target feature. And finally, we use the augmented data to retrain the original CNN model to derive the domain-adapted model. We evaluate the results against 4 baselines. Calibration uses a measured frequency response curve to convert the target microphone data back to the source domain and evaluate a pre-trained model. Second is used to perform the image translation. In this baseline, the audio features are treated as images. We train a second to map the microphone data back to the source domain. Conventional domain adaptation uses a 4 random microphones frequency response curve to augment the source domain data. The augmented training dataset is used to train a deep neural network and evaluate a 5th microphone dataset. Few-shot adversarial domain adaptation uses paired audio data from both source domain and target domain to obtain a domain-adapted model. Then evaluate this model on target domain data. Overall, PhyAug recovers accuracy loss from 50% to 70% on 5 microphone datasets. It outperforms other baselines with least target training data needed. Our second case study applies PhyAug on speech recognition model. We employ Baidu Deep Speech 2 model. It consists of 86 million neurons, which is 175 times larger than CNN model used in keyword spotting. This case study demonstrates the scalability of our approach. Prior mentioned baseline approach have not been evaluated on such complicated models. In this case study, audio data are first converted to spectrogram features and used to train a Deep Speech 2 model. The metrics used to measure the speech recognition model is word error rate. Deep Speech 2 recorded an oracle of 8% of word error rate on Libre Speech Clean Test dataset. Similarly, we use a speaker to play back the Libre Speech dataset and record them using the same set of microphones. This microphone dataset is then evaluated on pre-trained Deep Speech 2 model. We observe a 15 to 35% of absolute word error rate increase. The problem statement of this case study is how to explore the first principle of microphone frequency response curve to recover the word error rate of Deep Speech 2 model. The way we do the microphone profiling and use PhyAug for data augmentation is similar as case study 1, so we omit the procedure here and jump to the evaluation. For evaluation, we did not include a few-shot adversarial domain adaptation, as no prior research have successfully applied it on such complicated models, and the use of this technique requires significant change on original model. Second also failed to produce a reliable translation, as the training of second on spectrogram is far more complicated. Again, no prior research has successfully made second work for Deep Speech 2. The results show that our approach can reduce word error rate from 37% up to 70%. In conclusion, in this paper, we propose a physics-directed data augmentation to deal with the domain shifts governed by first principle in IoT sensing applications, and we successfully evaluate our approach on 3 case studies. Last but not least, we have made our source code, pre-trained model, and data available online. Thank you for your attention.